Good morning, students. Our today's topic is geodesic curvature. So first of all, let us define curvature vector. Let us consider this be a curve and P is any point on this curve. Let us take the vector R is the position vector of the point P. If we draw a tangent at the point P of this curve, then the unit tangent vector along this line, that is denoted by the vector t cap, and the derivative of t cap with respect to the arc length s, that is denoted by the vector r double dash, and this vector is called the curvature vector. Now let us find geodesic curvature. For this, let us consider this be a surface, and let us take P be any point on the surface, and let us take a curve to the point P. At the point P, let us take this vector r double dash. This is the curvature vector. Now let us resolve this curvature vector into two components. One component we have taken along the surface tangent. Suppose this is the surface tangent and this is tangent plane at the point P. Let us take this is a surface tangent and this is a surface normal. We have taken two resolved parts of curvature vector, one along the surface tangent and one along the surface normal. The component of curvature vector which we have taken along the surface tangent, that is called geodesic curvature vector, and that vector we have denoted by the vector kg, and the component of curvature vector which we have taken along the surface normal, that is called normal curvature vector, and that is denoted by the vector kn. So we can say that the curvature vector r double dash can be written as kn plus kg, where kn is normal curvature vector and kg is Gaussian curvature vector. Now let us find the values of both vectors. Now kn is normal curvature vector, and normal curvature by definition we already discussed in the previous chapter. Normal curvature is given by the formula kappa n into n cap. Now by the geodesic normal property, principal normal and normal to the surface are same. So this n can be replaced by the surface normal capital N. So the normal curvature vector becomes kappa n into n. Now let us find the value of geodesic curvature vector. Now the geodesic curvature vector that lies in the tangent plane, and also the vectors r1 and vector r2, these are the vectors tangential to the surface. It means the three vectors, vector kg, vector r1 and vector r2, these three vectors lies in the same plane. It means these three vectors are coplanar vectors, and we know that if three vectors are coplanar, then one of them can be written as linear combination of another two. So we can write vector kg as lambda r1 plus mu r2. These lambda and mu, these are called the components of geodesic curvature. So finally we can write the curvature vector as kappa n into n plus lambda r1 plus mu r2. Now let us find the values of lambda and mu, which are the components of geodesic curvature. So to find their values, let us take dot product of this curvature vector by vector r1 and vector r2. So firstly let us take the dot product of this vector by vector r1. So left side of this equation will become r double dash dot r1. On the right side, this will become kappa n into n dot r1 plus lambda r1 dot r1 plus mu r2 dot r1. Now n is normal to the surface, R1 is tangential vector to the surface. So these two vectors are perpendicular vectors. So their dot product will be 0. And R1 dot R1, that is the first fundamental magnitude E. And R2 dot R1, that is F. So this will become E lambda plus F mu. And we already discussed R double dash dot R1, that is denoted by capital U, where capital U is derivative of curl T by curl U dash minus curl T by curl U. So we have obtained U is equal to E into lambda plus F into mu. Now let us take dot product of this equation by the vector R2. So if we take dot product with R2 here, this will become R double dash dot R2 and kappa n into n dot R2 will be 0 plus lambda R1 dot R2 plus mu R2 dot R2. Now R1 dot R2, that is the fundamental magnitude F, and R2 dot R2 is G. So this implies V is equal to lambda F plus mu G. So we have obtained these two equations in lambda and mu. So by solving these two equations, we can obtain the values of lambda and mu. And lambda is given by Gu minus Fv divided by h square. And mu is given by Ev minus Fu divided by h square. So these are the components of geodesic curvature. Now, next there is a deduction. Now geodesic curvature vector Kg of any curve that is always orthogonal to the curve. In order to prove this, let us take the definition of curvature vector, which we discussed. By definition, R double dash can be written as kappa n into n plus Kg vector. Kg is lambda R1 plus mu R2. Now R double dash is curvature vector. By definition, curvature vector is given by the derivative of tangent vector with respect to the arc length s, yani dt by ds. Now by Serret-Frenet formula, dt by ds is k into n. So this equation becomes k into n is equal to kappa n into n plus lambda r1 plus mu r2. Now let us take dot product with vector t on both sides. So this will become kappa n into t is equal to kappa n dot t plus lambda r1 plus mu r2 dot t. Now n and t are mutually perpendicular vectors, so their dot product will be 0, and also n and t, these are also perpendicular vectors, so their dot product will be 0. So this equation becomes 0 is equal to t dot lambda r1 plus mu r2, and this is the curvature vector, geodesic curvature vector. So we get t dot kg is equal to 0. It means we can say that the vector kg is orthogonal to t. Vector kg is geodesic curvature vector, so we can say that geodesic curvature vector is orthogonal to the curve. Now next we find formula for geodesic curvatures. As we discussed here, that the vector kg, that is orthogonal to the vector t, and also because the vector kg lies in the tangent plane to the surface, so that is perpendicular to the surface normal. So we can say that this geodesic curvature vector is orthogonal to both vectors, vector r dash and vector n. Now because it is orthogonal to both, so that will be parallel to their cross product. So we can see that the vector kg is parallel to the vector n cross r dash. Now we can write the vector kg as its magnitude into its direction is given by this unit vector n cross r dash. So this value we have taken as the magnitude of curvature vector. Geodesic curvature vector means small kg is the magnitude of geodesic curvature vector capital Kg. Now substituting this value in the definition of curvature vector, r double dash is curvature vector which is kappa n into n plus kg. Substituting the value of kg here, we get r double dash is equal to kappa n into n plus the value of this is kg into n cross r dash. Now let us take dot product by the vector n cross r dash on both sides. So this will become n cross r dash dot r double dash is equal to kg into n cross r dash dot n cross r dash. Now because n cross r dash is a unit vector, so its dot product with itself, that will be 1. So we get kg is equal to the scalar triple product of the vectors n r dash and r double dash. So we have obtained the formula for kg. If we replace the parameters s by t, in that case kg can be written as the scalar triple product of n r dash r dot r double dot divided by s dot q. Now we can write it by using Lagrange's identity in the another form by substituting the value of n here. Because n is normal unit vector to the surface, by definition of normal unit vector, that is given by r1 cross r2 divided by h. Substituting the value here, this will become r1 cross r2 divided by h dot r dot cross r double dot divided by s dot q. Now by using Lagrange's identity for the dot product of these two vectors, by Lagrange's identity this expression becomes r1 dot r dot dot r2 dot r double dot minus r2 dot r dot into r1 dot r double dot or divided by h into s dot cube. Now in the normal property of geodesics, we derived these four values. The dot product of r dot with r1 is curl t by curl u dot. Dot product of r dot with r2 vector is curl t by curl v dot. Dot product of r double dot with r1, that is u, and dot product of r double dot with r2 is v. So we can substitute these four values here. We get the value of kappa g, which is given by 1 upon h s dot cube into curl t by curl u dot into v minus curl t by curl v dot into u. We can write this in terms of parameter s also. So if we replace the parameter t by s, this can be written in another form. So geodesic curvature is given by 1 upon h into curl t by curl u dash into v minus curl t by curl v dash into u. So these are the formulas for geodesic curvatures. We can write another form of geodesic curvature also by using this relation. From this relation we can find the value of either u or v, and we can substitute here. This relation is u dash into u plus v dash into v is equal to 0. So from here, if we find the value of u, this is given by minus v dash v divided by u dash. If we put this value here in this equation will become kappa g is equal to v upon h u dash into u dash curl t by curl u dash plus v dash into curl t by curl v dash. Now as we already discussed, this t is homogeneous function of degree 2 in u dash and v dash. So we can use Eyelets theorem for homogeneous functions. So by that theorem, u dash into curl t by curl u dash plus v dash into curl t by curl v dash is equal to degree of t into t. Degree of t is 2, so this will become 2t, and 2t is equal to 1, which we discussed already. So substituting this value here, this is 1, so kg will become v upon h u dash. So we have obtained the value of geodesic curvature in terms of u, and in terms of v also we can find the value of geodesic curvature, which is given by kg is equal to negative of u divided by HV dash. So these were the formulas for geodesic curvature which we will use in the numerical problems.